So when we talk about kinetic theory of particles, we basically mention that everything is made of particles. That's the very first thing that we have. And that's where we will begin, that everything is made of particles, and these particles are all free from each other. They are very far apart and all that. So that is the first idea, that gases, that state is called gas. So they're made of tiny particles in random motion. That's the first thing we have to understand. Second thing, these particles, because they're moving, obviously that motion will have some kinetic energy associated with it. And the second idea that we have for gases is that their average kinetic energy, the particles, their average kinetic energy of the particles is directly proportional to the temperature of the whole gas. So this is the first connection that we have between those particles and the overall substance. So we're saying that the substance is the huge thing made of these tiny particles, but the kinetic energy of these particles, the average of that tells us the temperature of the substance. So you can technically measure the temperature and get an idea of what the average kinetic energy is. And if the temperature rises, average kinetic energy of these particles increases. And if the temperature falls, then average kinetic energy of these particles decreases. This is very powerful because individual particles cannot have temperature. They can just have kinetic energy. But together, their average determines the temperature, which we can easily measure. So that is the first thing we have where we can make a connection with the tiny particles that they are. The third main idea of ideal gases is that the particles, obviously, they're moving around. So it is inevitable that they'll collide with each other. So when they collide, the collisions are perfectly elastic. Now, what does that mean? Elastic collisions, in fact, any collision will have conservation of momentum. Momentum is a way of understanding the motion of stuff. So we're saying that m times v, that's the momentum. And when one thing collides with the other, the impact is that that momentum is transferred to that thing. It is also possible that because we have law of conservation of momentum, all the momentum of that thing will be conserved, which means that while one particle may lose some momentum to another particle during a collision, overall momentum remains the same. And that is true for any collision, regardless of whether it's elastic or inelastic. But elastic collisions have another thing. Elastic collisions mean that when particles collide with each other, they don't slow down. Or if they speed up, the other slows down proportional to that. The overall kinetic energy of the system remains the same. So not only are these collisions going to conserve momentum, obviously any collision would, but their individual kinetic energies may change, but two kinetic energy of the other thing. So that's very important. We already have said that kinetic energy, the average of that is related to temperature. And now we are saying that that kinetic energy remains in the form of kinetic energy. It may go from one particle to another, but it will not go from kinetic energy to potential energy or elastic potential energy or sound or light or any other form. It is going to remain kinetic energy, but may bounce from one particle to another particle to another particle. Overall kinetic energy remains the same. And that is interesting because while we know that everything conserves momentum, every system conserves energy, this is a special case where not only is energy conserved, the type of energy is also the same. It is kinetic energy and it remains that way, which means overall temperature does not change during the collisions. And that's the major implication of this idea, that when particles collide, they do not lose energy in the form that overall temperature slows down. Because otherwise, everything, because it's moving randomly, particles will collide, and eventually, if they had inelastic collisions, they will lose that energy that they have and cool down. But ideal gases don't have that. Ideal gases imply that the collisions are perfectly elastic, which means kinetic energy of one particle may change to kinetic energy of the other particles. They may stick together during collision. They may collide and slow down, but the other speeds up. But in all of that, overall average remains the same because overall kinetic energy remains. The fourth main idea of ideal gases is that these collisions will affect and obviously produce pressure. It's not really a separate idea from this one. It's just related to this, that these collisions give rise to or produce pressure. And these collisions are not between just the particles themselves, also with the walls of a container. Because if you do not have a container, you don't have a closed system, you don't have a way of measuring the pressure. So pressure depends on having a closed system, and the walls of the container make it a closed system. So what's ideal gas? Ideal gas is anything that behaves in three different fashions. Number one, there are tiny particles, all free from themselves, in random motion. So tiny particles independent from each other, which means there are absolutely no forces. And that's interesting because we just finished bonding, which was all about forces. And now we're saying there's no force, but let's just play along. So no forces. Why is that important? It's important because if particles were to have a force of attraction, then when one particle comes close to the other particle, it will get attracted by that one and will not bounce away. And in terms of losing, like bonding with each other or coming close to each other, they may lose their kinetic energy and maybe slow down. But because our third idea, that collisions are elastic and kinetic energy of the system remains the same, it implies that that can't happen. The forces of attraction cannot exist. So here's the radical idea of particles. They're free to move around. They are randomly moving all the time. There's no force of attraction between them. They have average kinetic energy, which is an indication of the temperature. Their collisions are perfectly elastic. And how tiny are these particles? The size of particles is very, very small to the volume of the gas. So remember, there were three main things when we were talking about particles and gases. There was the volume of the gas, there was temperature of the gas, and there was pressure. So now here we have a connection with the individual particles, that we're saying temperature is dependent on the kinetic energy of the particle, average kinetic energy of the particle. Pressure depends on the collisions between particles and the container. And volume is so huge, which is basically the distance between these particles, that the size of the particles makes no difference or does not affect it. So if I were to, let's say, take up volume of every individual molecule and compare that to the total volume of that gas, it will be so huge, the volume of the gas, that that volume of molecule will have no effect. Because you know that we can assume molecules to be circular or spherical or oblong in some cases, but the size is so small that individual particles are negligible compared to the distances between them. Malab, over here right now, I have, this is a closed system, let's say. Okay. And in this system, I have these three molecules. And these three molecules, their individual volume, if I were to just connect them over here and make a small area and find the volume of this triangle, then that volume is negligible compared to the volume of this whole container in which I have gases. So this is the main theory that we have, that particles of the gases are small. They're so small that their volume, even if you add it all up, is negligible to the volume of the gas. Second, the kinetic energy, average kinetic energy of these particles is directly related to temperature. So if you are increasing the temperature, it implies you're increasing the average kinetic energy. The collisions between these particles are elastic, which means that overall kinetic energy remains the same, but because there's no force, they will just come and bounce back. And that means that you're basically giving a rise to what the pressure is. So that is the main concept of what an ideal gas is supposed to be like. Of course, ideal gases are just a work of fiction. They don't really exist. but that's fine. Now, let's look at that temperature. We have a specific scale for that temperature, and that is Kelvin. Now, judging by this idea that kinetic energy, average kinetic energy of the particles is directly proportional to temperature, what does 0 Kelvin mean? So average kinetic energy is directly related to temperature, and temperature in Kelvin specifically. So when I say I have 0 Kelvin temperature, what would that mean? It simply means that average kinetic energy is also 0, which means the first idea, the tiny particles that are in random motion, will be falsified. And no wonder it's almost impossible to actually get 0 Kelvin temperature. Now, judging by the same idea, can we have negative temperature? What do you think, Meher?
Sir, I don't think so, because negative kinetic energy क्या होती है?
Exactly. Negative kinetic energy makes no sense because it's a scalar quantity. It can't be a vector quantity. Otherwise, we would say, okay, it's energy in the other direction. But it's a scalar quantity. So negative kinetic energy kuch nahi hota. So temperature can't be negative, and technically it can't be 0 either, because you may strive for 0, but that means particles are all just stopped right where they are. They have 0 average kinetic energy. जिसका मतलब क्या है कि वो रुके हैं, they're not moving anymore. So उससे ज्यादा उनको slow down तो नहीं आप कर सकते. So that means if you speed them up, if you give them more kinetic energy, then temperature will rise. So higher the temperature, higher the kinetic energy of that particle, the average kinetic energy of those particles. But I keep saying average because kinetic energy of all the particles in the gases is not individually the same. Every particle has different kinetic energy, and there's a whole distribution of that kinetic energy. We call that Boltzmann distribution, that how our individual energy, how is it distributed? But the average relates to the temperature. So understanding these 4 or 3 main ideas leads us to 4 gas laws. And we talked about those gas laws yesterday. So the first one was Boyle's law. Then we had Guy-Lussac's law. Then we had Charles' law. And then we have Avogadro's law. Now, these laws basically say that you have 4 things. You have volume, temperature, pressure, and number of gas particles that you have. And all of that is related to each other. If in isolation, you can take 2 of them at a time. So then I'll say that Boyle's law says that pressure is inversely related to volume. And Charles' law says that volume is inversely related, directly related to temperature. And Guy-Lussac's law says that pressure is directly related to temperature. And Avogadro's law says that, and Avogadro's law says that the volume of these particles is directly related to the number of moles of these particles. Now, let's break it down one by one. Boyle is saying pressure is inversely related to volume, which means if they collide more, then they're closer. That's what it means. And that makes sense, right? But only in the case when temperature doesn't change. And also the number of particles doesn't change. So there's always some constant. You can't just pump in more gas molecules and be like, oh, I've broken the Boyle's law. Because you are not following the requirement of Boyle's law. You can't add more particles. You're talking about the same amount of particle at the same temperature, which means average kinetic energy remains the same. And then if you pull them close together, pressure will rise because they collide more. If you take them far apart, they will collide less. Obviously, they will collide less. Why? Because their kinetic energy is fixed. Temperature is fixed, which means that if they're close to each other and they're moving towards each other, obviously unko time kam lagega with same kinetic energy. But if they're far away from each other, usko time zyada lagega, which means your pressure will decrease automatically. You have increased the volume. Now, Guy-Lussac's law says that pressure is directly related to temperature when volume and number of mole is constant, which means I'm not changing the size of my container. The size is not changing. So now these particles are in trapped in this box. And then there is one particle, then there's the other particle, and this is moving towards it. If I give it more kinetic energy, it will collide faster, it will collide more. Obviously, it will, because now it's moving faster and they're closed in a certain uh, space that they have. So obviously they're going to collide more. अब उनको दूर तो जाने नहीं दे रहे, so वो क्या करेगा, एक दूसरे से strike ही करेंगे ना. And Charles' law says that volume is directly related to temperature if pressure and number of mole is the same. And that is also true, because if I'm saying that particles will collide at a fixed rate now, then if I increase the temperature and I don't want them to collide more, so what will they do? They will have to go further away from each other. Because if I want them to, let's say, collide 1 time a second, then something moving at a faster speed should be coming from further away, so that it collides 1 time a second. So that's Charles' law, that volume is directly related to temperature. You increase the kinetic energy of particles, you increase the distance between them, because obviously they'll collide, go further away, they'll bounce further away. That's the same, no problem. And Avogadro's law, you have been using it, you might not have noticed, but in moles in O levels, you used to say that volume ratio is same as the moles ratio. And why is that? Because V1 over V2 will equal N1 over N2. That's Avogadro's law. So you used to compare moles of different gases using this. So you have been using it. It simply says if you add more particles in, but you're not allowing them to collide more, and you're not allowing them to change their kinetic energy, average kinetic energy, then they will go. If you add more particles, you have to move them further away. And that's fine, because if you have add more particles and you don't want them to collide more than a fixed amount, then they will be further away. So they cover the distances in a way that pressure same aa jaye. And these 4 laws in isolation work for ideal gases. But what if I were to change multiple things at a time? Then I will have to look at something else. And that is my ideal gas equation. What's ideal gas equation? We talked about it yesterday. Ideal gas equation simply sums all of these laws together. So ideal gas law says that PV equals nRT. Now, where is R coming from? R is basically the gas constant, which again is coming from 2 things. R is Avogadro's number, which is number of particles in 1 mole, multiplied by Boltzmann constant. And Boltzmann constant is again something that determines the relation of these gases or the particles. So the value of R is 8.31 joule per Kelvin per kg, I think. Yep. It is given in the exam. Joule per Kelvin per mole hoga, not kg. Yeah. This is the ideal gas constant, which means that 4 things will work in unison to give you the constant again. So PV over NT will always equal R. So no matter what gas you have, as long as it's behaving ideally, pressure, volume, number of moles and temperature will work together to give you 8.31 as the answer. And that's remarkable. Why does it work like that? Or how do we know that that is the case? That's beyond the scope of this syllabus that we have. Now, here's the thing. The units are important, because in this case, we are working with SI units, and this is ideal gas law. So what are the units? The units are that pressure, SI unit, pascals. Volume, SI unit, meter cubed. Number of moles, obviously mole. R, wo bata diya. And temperature in Kelvin, which means you need to be able to convert. Pressure, usually it's given in pascals or atmospheric pressure. So the key to remember here is that 1 atmospheric pressure is 100,000 pascals. Okay, roughly. And volume is in meter cube, but we usually work with cm cube or dm cube. So just remember that. How do you convert things like that? So remember that 1 centimeter is equal to 100. 1 meter is equal to 100 centimeters, right? So if I were to cube this thing, then I'll cube this thing, which means 1 meter cubed is equal to 100 cube centimeters, which is 1,000,000 centimeter cubed. Usually ऐसा नहीं लिखते, 3 के बाद लिखते हैं. So yeah. So a million centimeter cube, that's what it's equal to. Similarly, 1 decimeter is equal to 10 centimeters. So if I were to cube it, I'll get 1 decimeter cubed is equal to 1000 centimeter cube, which I think you know already. So that's how you related that 1 meter cubed is a million, 1 into 10 power 6 centimeter cube. Number of moles is moles, and temperature in Kelvin. And usually we work with degrees Celsius in this part of the world. So degrees Celsius, you just have to know that 0 degrees Celsius is 273 Kelvin. And again, this is not something that you can multiply or ratio. It doesn't work as a ratio. You simply have to add them. So if I give you 20 centimeters, 20 centigrade, then you have to add it to 273. So that means at room temperature, which is 25 degrees Celsius, the temperature is going to be 25 plus 273, which is 298 Kelvin. Okay. So it's important to know that your units are important when you're using ideal gas law. So let's do an example from your book. So the book says there's this scenario where you have a gas situation and you want to know the volume of the gas. Okay. Calculate the volume. So volume is unknown. Occupied by 0.5. So number of moles is 0.5. Now, why have they given us 0, 0 at the end? What's the significance of that 0, 0? Is there any difference in that 0.00500 and 0.5? In dono numbers mein koi fark hai? What do you think?
Sir, I think they're sort of the same, but 0.500 tells me that 5 ke baad there's no other number but 0, 0. And
Doesn't this tell
0.5.
you the same thing? Or is there a
No,
hidden
but
number
like
somewhere?
I don't know 5 के आगे क्या हो सकता है.
Good, good. So this gives us an assurity that it's exactly that, which means that my number 0.5 here is less precise and this is much more precise, because वो मुझे बता रहा है कि I have measured it to 3 decimal places. So the machine I'm using is really good. The chances of error is really small, because अगर मैं इसको लूँ ना तो मेरा error बनता है 0.05 over 0.5, which is I think 10%. But अगर मैं इसको लूँ तो मेरा error बनता है 0.0005 over 0.5, which is 0.01%. So मेरा error काफी कम है. So as far as experimental prowess is concerned, 0.500 shows कि भाई मेहनत से काम हुआ हुआ है. Of carbon dioxide, the identity of the gas is irrelevant at this point. We are assuming it to behave as ideal gas. At a pressure of 150 kilopascals, so pressure is given, pressure is 150 kilopascals. Is it more than atmospheric pressure or less? It is more, because atmospheric pressure is 100,000. Yeah. So, and lastly, the temperature is 19 degrees Celsius. And 19 degrees Celsius, I can convert it and I'll add 19 to 273. So 19 plus 273 is 292. Yep, 292 Kelvin. साथ साथ उसको convert कर लिया. Don't wait for the final answer. And now I want to find volume. Volume is going to be nRT over P. So N is 0.5, R is 8.31, 292 over 150 into 10 power 3, because kilo is 10 power 3. And there you go. Once you substitute the values in there, you get your answer, which is 8.09 into 10 power minus 3 meter cubed. So this is the answer in standard form, which I can simply convert to decimeter cube, because 10 power minus 3 is decimeter cubed. So मेरे पास आ गया. Okay. Now I can use this ideal gas equation to not only find number of moles, but also MR of a certain gas. मतलब अगर मेरे पास ये सारी information given हो और मुझे moles का वो ना बताए, तो कोई मसला नहीं है. I can still identify that this is carbon dioxide. Because now that I know the volume, the temperature, the pressure, everything, I can now technically find out MR. And from MR, I can find out kya mass hoga, kis tarah hoga. So you can do it using these equations. So let's suppose we have an unknown gas. बल्कि अभी उस पे नहीं जाते. Let's keep things simpler. Let's say we now again know that this is oxygen gas. So यहाँ पर this is another question. Go on, do it. बहुत आसान है. I just need you to work on unit conversion and all that. While it's really easy to just plug in the numbers and all that, a couple of important ideas here. For example, if you have volume in, PV, right? So if I had pressure in kilopascals and I have volume in decimeter cubed, then this deci is 1/1000 meter cubed. And this kilo is 1000 pascals. So kilo is 1000 times pascals and deci is 1/1000 meter cubed, which means that I can simply cut them out. So that's a pretty neat shortcut, that if you have dm cubed and kilopascals, you don't need to convert them. Just put them right in there because they will take care of themselves and the equation will still work. So that's a good thing to keep in mind. Now, here's the thing. While we can use ideal gas equation to find that, number of moles is still the number of moles we know from O levels. So it is the good old mole, and we can convert it to mass over MR if we ever need it. We can convert it to number of particles over Avogadro's number if we need to, which means that I can use ideal gas equation to find MR, or find, if I have the MR, find the mass of that thing. I can find number of particles involved, or I can easily confirm Avogadro's number through this. Of course, I wouldn't suggest doing that because technically you're not confirming it. You have basically glitched the system. So क्योंकि ideal gas law depend ही Avogadro's law के ऊपर करता है, तो it's just like begging the question. So you can find mass, MR, वो सारा कुछ from ideal gas equation. Okay. So another question that they usually ask is about the graphs, that how does PV compare to volume of the gas? Now, how does that work? Yahan par they haven't told us what the volume is. They've just told us to draw the graph. Now, PV and volume, how does that relate? So PV against V should be something like this because it would be inversely related to that. But PV against P should be a straight line, because no matter how much I increase the pressure, volume would adjust accordingly. It will come closer, closer, and closer, so that I end up with this graph. And this is a graph that they usually ask you about in the exam. What will be the graph of PV against P, or what will be the graph of PV against V, all of that. तो इसमें आपको बस यही ध्यान में रखना है that if you increase the pressure, because as you go to the right of the graph, you're getting higher and higher pressure, then pressure, no matter how high the pressure is, PV will still be constant. And that reminds me, this should also be a constant then. So P into V for any ideal gas is a constant, right? Provided temperature bhi aapka constant rehta hai. Okay, so now we know how the total gas behaves. What about portions of a gas? And that brings us to Dalton's law. Dalton's law says, and Dalton was an English teacher, by the way. English language padhata tha. Dalton's law says that you take any portion of the gas and the collisions of that portion are directly proportional to the fraction of that portion. मतलब अगर मेरे पास ये पूरा container है, and in this container I have gases moving around, and I take just this part of it. Let's say this part is 1/9 of the total. Then जो भी particles होंगे, उनकी collisions होंगी, the collisions of this 1/9 portion are 1/9 of the total. Malab, you can take this portion and take it out, and its pressure will be proportional to the pressure that was when it was part of this whole thing. And that is why this is called Dalton's law of partial pressure. Because all I'm saying is that collision of particles is the overall pressure that I'm getting is a combination of individual particles that you have. And of course, that is like a no-brainer. That is true. इसका मतलब ये हुआ कि अगर मेरे पास pressure है, total pressure, then it is the pressure of one portion of the gas plus pressure of the total portion, second portion of the gas, and the plus pressure of the third portion of the gas, and so on and so forth. This is important because इसका मतलब ये हुआ कि अगर मैं pressure of the one portion of the gas compared to total pressure करूं, तो it is going to be equal to the number of moles of that portion compared to the total number of moles, because pressure is coming from total number of moles colliding with each other, which means this is by the way called partial this is called mole fraction, and this is called partial pressure. So let me take the example of air. Air is 21% oxygen, which means that for every 100 particles you have in air, pure air, वैसे it's an oxymoron, but I'm saying unpolluted air. So in unpolluted air, you have 21% oxygen, you have 78% nitrogen, and then rest of it is argon, carbon dioxide, and so on. Then उसका pressure, atmospheric pressure होता है 100,000 pascals. So according to Dalton's law, because the number of moles of oxygen out of the total gas is simply 21%, then the pressure because of oxygen is also 21%, which means the partial pressure of oxygen is going to be 21% of 100,000 pascals, which comes out to be 21,000 pascals, which is pretty neat. Which means that if I were to, let's suppose, take all the oxygen out from the air, so air pressure फिर कितना होगा? It will be 79% of the total pressure, which is 79 kilopascals. So if you take all the oxygen away from the atmosphere, तो पीछे pressure कितना बचेगा? जितना अपने mole fraction लेके गए हैं उस लिहाज से. So if you want to know that you have a mixture of different gases and you want to know what's the contribution of any particular gas, the contribution is proportional to how many particles it has over there. And obviously, जितने ज्यादा particles होंगे उतना ज्यादा collide करेंगे, बात खत्म. ये बिलावल भुट्टो वाली बात है, ज्यादा particle है तो ज्यादा pressure होता है और कम particle है तो कम pressure होता है. So Dalton's law simply tells me that in any mixture of gases or even pure gas, you take a portion of that gas, the mole fraction tells us the contribution to the total pressure of that part, whether it's a portion of pure gas or whether it is a total gas that you have overall. ठीक है? So let's say मेरे पास this scenario exists. I have mixture of multiple gases and this is the situation. 80 grams of oxygen, 140 grams of nitrogen, 44 grams of carbon dioxide, and 60 grams of argon. And the total pressure is 3.6 into 10 power 6 Newton per meter square, which is nothing but pascals, right? Okay. Calculate the partial pressure of each gas. कोई मसला नहीं है. Let me first figure out the number of moles. So number of moles of each gas: oxygen, nitrogen, carbon dioxide, argon. Oxygen is 80 over 16. सही किया मैंने?
Sir, do you have to convert it to kg?
No, I don't have to convert it to kg because I'm looking for moles, but I need to make sure that my MR is the same. I'm not talking about the oxygen molecule. I'm not talking about oxygen atoms. I'm talking about oxygen molecule, which is 32. And then I have 140 over 28 for nitrogen and 44 over 44 for carbon dioxide and 60 for 20 of argon. No, argon is 40. I'm sorry, I don't have priority. Acha. So let me figure this out. 80 divided by 32 is 2.5. So that is 2.5 moles of oxygen. And this I think is 5 moles of nitrogen, 1 mole of carbon dioxide, and 2 by 3 moles, no, 3 by 2, 1.5 moles of argon. So the mole fraction, the total moles that I have, let me just add it up. So 2.5, this is 10 moles, right? So mole fraction Let me find that. So 2.5 over 10 out of the total number of moles I have, oxygen is 1/4. Out of the total number of moles I have, nitrogen is 1/2. Carbon dioxide is 1/10. And argon is 1.5 over 10, which is 15%. Yep. So 0.15. So this is the mole fraction, which means total pressure में से इनकी contribution कितनी है? जितने ये percent है. So total pressure है 3.6 megapascals. So let me just multiply it. So 3.6 megapascals, 3.6 divided by 4, that is 0.9. So 0.9 megapascal will be because of oxygen, and 1.8 megapascals will be because of nitrogen. 0.36 megapascals will be because of carbon dioxide, and the remaining, whatever that is, 3.6 times 0.15, that is 0.54. 0.54 megapascals will be because of argon. So Dalton's law is pretty simple. You take any mixture of these gases, the mole fraction that they have, like how many particles of that thing exist compared to the total particles that you have, will determine the contribution of that thing to the overall pressure. And this is super important when it comes to understanding gaseous mixtures, because वहां पे let's suppose, बड़ी सिंपल सी बात है, let's suppose आपके एग्जाम की तैयारी नहीं है और you want to just do the best you can in the limited time that you have. You will obviously focus on the parts that are having the higher weightage. मतलब आपके टीचर आपको कहते हैं कि बेटा बॉन्डिंग पे 60% पेपर आना है, so you'll probably just leave everything out and focus all your efforts on making sure that you get that 60%, because that's the thing that matters the most. And that is because उसकी weightage हुआ है. इसी तरह यहाँ पर the nitrogen had the highest contribution to the total. उसकी weightage half थी पूरे का. So obviously उसका pressure भी half है पूरे का. So that's Dalton's law of partial pressure. So we have 5 laws so far, and all of them are fictional because they don't entirely tell us how gases really behave. क्योंकि there is one small problem. शुरू में हमने जो बातें की हैं, that there are tiny particles in random motion with no forces of attraction, really no force of attraction. And then we are saying collisions are perfectly elastic. कहाँ elastic होती हैं collisions? Particle पास आएगा, temporary dipole बनेगा, वो जाने नहीं देगा उसको. Definitely slow down करेगा, definitely kinetic energy कम कर देगा. And then it's saying average kinetic energy change ही नहीं होती, क्योंकि overall kinetic energy is conserved. ऐसे थोड़ी होता है. इस तरह तो सारे रेफ्रिजरेशन खत्म कर दो भाई. एक दफा कोक ठंडी होगी तो सारी उम्र के लिए ठंडी रहेगी. And size of particles is very, very small compared to volume of gas. Sure, that might work for large containers, but what if I'm talking about microscopic scale? तो फिर तो state change भी नहीं हो सकती इस तरह तो. तो ये सारी बातें जो हमने की है ना, we are in some imaginary realm जहाँ पे हमने सारी बॉन्डिंग, चार्जेस, डिस्ट्रीब्यूशन ऑफ इलेक्ट्रॉन सबको उठा के खिड़की से बाहर फेंका और हमने कहा बेटा ये जो बात कर दी है ना मैंने, बिल्कुल ठीक बात कर दी है. Turns out it does not exist. This does not tell me how reality behaves. तो फिर मैं क्यों पढ़ रहा था इसको? Because it does tell me that reality will now deviate from this thing. So this is the base from which every real gas will deviate. तो और कुछ ना करे, वो ये करेगी और फिर इसमें थोड़ी इख्तरा करनी होगी. It will change a little in its behavior from these things. And if we understand these things, we understand how it should behave ideally, and then we can predict the behavior of a certain gas. If we know कि अच्छा उसमें forces इतनी है तो उससे ये फर्क पड़ेगा, उसमें kinetic energy, elastic collision इतनी ज़्यादा नहीं होती तो उसमें ये फर्क पड़ेगा. So that is why this model is very all right.